In this video, I'm going to discuss the basics of motion in 2 and 3 dimensions. Specifically, I'll be focusing on projectile motion, which is a special case of two-dimensional motion. For motion in 2 or 3 dimensions, if the acceleration is constant, you can use the equations for constant acceleration just like we did with one-dimensional motion, but you do it for x, y, and z separately. We're going to be focusing on just two-dimensional motion, so we're only going to have things with x and y. And so, just as before, the best way to do things is to set up a table to organize things, listing out all the variables. The difference is you need to do this for both the horizontal and the vertical direction. So you set up a horizontal column, and just like before, you list the initial position, the later position, the initial velocity, the later velocity, the acceleration, and the time. The difference is, with this initial velocity, this will only be the x component of the initial velocity. In general, the initial velocity will be at an angle, and you'll break that into components. It's a vector that you'll break into x and y components. And so v0x is the x component of the initial velocity. And then we have the later velocity vx, which is the x component of the later velocity v. And when we talk about the acceleration, we're only going to look at the acceleration in the x direction if we're looking at the horizontal motion. And then our final variable is the time t. And then we would set up a vertical column. Instead of the position along the x-axis, x0, we'll have the position along the y-axis, y0. So that's the initial height. We'll have the height at some later time t. Again, for the initial velocity, if we're looking at the vertical motion, all we care about is the y component of the initial velocity. And vy, that's the y component of v. Just like vx was the x component of v. And again, when we talk about the acceleration, we specifically are only looking at the y component of the acceleration. And again, we have the time. And so with these constant acceleration problems, we turn this into two separate one-dimensional motion problems. We look at constant acceleration in the x direction, and we look at constant acceleration in the y direction, and then we'll put those two things together. But the important thing is when we're looking at the horizontal motion, we only look at horizontal quantities. You need to make sure that you only use the horizontal component of the initial velocity. You need to make sure that you use the horizontal acceleration. A common mistake is for people to mix their horizontal velocities and their vertical accelerations and put everything all together. You need to make sure that you're only using the horizontal quantities for the horizontal motion, and you're only using the vertical quantities for the vertical motion. So we're going to specifically talk about projectile motion. And so projectile motion is, the definition of projectile motion is two-dimensional motion where the only force acting is the force of gravity. So with this means we're ignoring air resistance. We're going to assume that things are shot in a vacuum, or that the air resistance is small enough that we can ignore. Now this definition might seem familiar. Earlier, when we looked at one-dimensional motion, we talked specifically about free fall. And the definition of free fall was one-dimensional motion where the only force acting is the force of gravity. Projectile motion is the two-dimensional version of that. In fact, free fall is the special case of projectile motion where there's no horizontal motion, where it just goes straight up and straight down. Projectile motion is the more general case where it's moving horizontally, but again, the only force acting is the force of gravity. So in projectile motion, the horizontal motion and the vertical motion are independent of each other. Neither motion affects the other. How fast it's moving horizontally has no effect on how fast it's moving vertically. How fast it's moving horizontally has nothing to do with how long it takes to reach a certain height or how long it takes to reach the ground. So if I have a projectile with an initial velocity v0 at an angle theta sub 0, again, we'll use this subscript 0 for the angle because the angle changes in the flight. If you look at this diagram that's on here, this initial angle is a certain value, and then as this moves through the air, that angle changes. At this highest point, it's only moving horizontally, and then the angle changes, so now it's below the x-axis, and we have this angle. So as time goes on, the angle changes. So to represent the fact that we're looking at the angle at the very beginning, we put the subscript 0 on it, just like we did for v0, just like we did for x0. So if I have an initial velocity v0 at an angle theta sub 0, I can take that velocity and I can break it into x and y components. This x component of the initial velocity, v0x, that's the side adjacent to that angle theta. Cosine is adjacent over hypotenuse, so v0x is going to be that initial velocity v0 times the cosine of that angle theta sub 0. And this y component, v0y, that's the side opposite theta 0. Sine is opposite over hypotenuse, so v0y is the initial velocity v0 times the sine of theta 0. So in this picture, when it says that v0x is v0 cosine theta 0 and v0y is v0 sine theta 0, all that's saying is if you have a velocity that's at an angle, you break it into x and y components. So that's all that is referring to is take a vector, find the x and y components of that vector. In the horizontal direction, there's zero acceleration. This is a key thing. Because the only force acting is the force of gravity, and the force of gravity acts straight down, in the horizontal direction there's no acceleration. There's nothing pushing on it or pulling on it horizontally, so there's no acceleration in the horizontal direction. In the vertical direction, there's a constant downward acceleration. So that acceleration is negative g, or putting numbers in on Earth, that would be negative 9.8 meters per second squared. So in the vertical direction, the acceleration that we have is exactly the same acceleration that we had in free fall. In the horizontal direction, there's no acceleration. It's just something that's moving at a constant velocity in the x direction. That picture that's showing the path of the ball and the velocity at the different times, we're going to return to that in a later slide and talk about it in a little bit more detail. And so this picture shows a cannon launching a cannonball off the top of a very tall cliff. And this cannon is firing the ball horizontally at 20 meters per second. Its initial velocity, v0x, is 20 meters per second. Because it's not moving at all in the y direction, the y component of its initial velocity is 0. So again, if a vector is only in the x direction, it only has an x component, there's no y component. And in this picture, we can see that because there's no acceleration in the x direction, at any time during its path, that x component stays 20 meters per second. The x component of the velocity does not change. But in the y direction, it is accelerating. So this is showing the cannonball at approximately 1 second intervals. It's a little over 1 second. So at that first time, the velocity went from 0 to negative 10 meters per second in the y direction. Again, in 1 second, it's going to gain 9.8 meters per second in the downward direction. So this is a little over 1 second. And a little over 1 second later, it goes from negative 10 meters per second to negative 20 meters per second in the y direction. And then it's negative 30, and then it's negative 40 meters per second, and then it's negative 50 meters per second. In the vertical direction, the velocity is changing. That's what it means to say that it has an acceleration of negative 9.8 meters per second squared in the y direction. Now, we also can see that we have an x and a y component of the velocity at each time. And so at any time, we could calculate the total velocity of the object. Not the x component, not the y component, but the total velocity of the object. And so let's look at the total velocity of the object right before it hits the ground. Right before it hits the ground, it has an x component of 20 meters per second, but it has a y component of negative 50 meters per second. And so the way that we would find that total velocity is I would draw these vectors using the tail to tip method. So I draw my x component of 20. I draw my y component of 50 meters per second downward. And so if I want the resultant vector, I'm looking for that hypotenuse, which is the square root of 20 squared plus 50 squared. And so that velocity has a magnitude of 53.85 meters per second. This is the magnitude of the velocity. This is also the speed of the object. If a question is asking about the speed, they're referring to the magnitude of the total velocity. Not the x component, not the y component, but it's the magnitude of the overall velocity. Again, when we first were defining velocity and speed, we said that speed is the magnitude of the velocity. So the velocity vector, that's that overall resultant vector, the 53.85 meters per second. A vector has a magnitude and a direction. In a second, we're going to calculate the direction. But the magnitude of that vector, 53.85, that is the speed of the object. If I want to find the direction of the vector, because again, a vector has a magnitude and a direction, I would calculate that angle. Again, I know the opposite side. I know the adjacent side. So the tangent of that unknown angle theta equals the opposite side 50 over the adjacent side 20. So that angle is the inverse tangent of 50 over 20. Again, if the tangent of theta equals 50 over 20, I want to undo the tangent function, so I use the inverse tangent function. So in your calculator, if you calculate the inverse tangent of 50 over 20, you get an angle of 68.2 degrees. And that angle, I can see in the picture, that angle is below the x-axis. So right before it hits the ground, the velocity has a magnitude of 53.85 meters per second, and it's moving at a direction of 68.2 degrees below the horizontal, or below the x-axis. Okay, so on this slide, I want to talk a little bit about some of these ideas of projectile motion. And we're going to look at these a little bit more in the next slide as well. So in the horizontal direction, because the acceleration is 0, the horizontal motion is exactly equivalent to a ball rolling freely along a level surface. As something rolls freely along a level surface, it moves at a constant velocity. So in this animation off to the right, you see that green object. That's the gravity-free path. If it was just rolling along a table, or if it was just moving and there was no gravity pulling down on it, that ball would just move in a straight line, and it moves at a constant velocity. You can tell the velocity is constant because the spacing every fraction of a second. So maybe those dots represent every tenth of a second. So every tenth of a second it travels the same distance in the x direction. And so that's what it means to say that the horizontal velocity is constant. In the vertical direction, it's exactly equivalent to an object in free fall. The only force acting is the force of gravity. The vertical component of the velocity changes with time. And so the red object in this animation, that would be an object in free fall. It just falls straight down, but that is accelerating because that distance that it travels each fraction of a second, each tenth of a second, keeps getting bigger and bigger and bigger. So it's going faster and faster and faster. And then that blue path would be the actual path of the projectile. So this is something that was moving horizontally at the beginning, and it starts to fall down. But as it falls down, it continues to move in the horizontal direction. And so its horizontal motion is exactly equivalent to that green object. Its vertical motion, its vertical position is exactly the same position it would be at if it was in free fall. And so if you put those two things together, you get the overall path of the object. And again, this path is going to be a parabola, which we're going to see on the next slide. So that animation goes a little bit quickly, so I want to look at it a little bit more slowly, just piece by piece. So let's say that I have a table, and I have a ball that's going to roll along that table. So it's moving horizontally as it rolls along the table. If there was no gravity, that ball would just move at a constant velocity. Or if this table extended farther to the right, it would move at a constant velocity. Again, we can see that that velocity is constant because each second it traveled the exact same distance in the horizontal direction. And now we're going to look at the ball falling straight down off the edge of the table. Not moving horizontally, but just falling straight down. We're dropping the ball from the edge of the table. So as it falls downward, it travels a small distance, and then a bigger distance, and then a bigger distance, and then a bigger distance. That's something that's accelerating. That's what free fall looks like. Projectile motion is going to put those two things together. If you look, the horizontal position is exactly the same horizontal position that it would have had if it kept rolling in a straight line, but its vertical position is the same as if it was in free fall. So again, if each of these dots represents 1 second, 1 second after this rolled off the table, the horizontal position of the ball would be here, but the vertical position of the ball would be here. And so when you put those two things together, you get this ball in this location. At 2 seconds, the horizontal position of the ball is here, but the vertical position of the ball is the same as it would be when it fell straight down for 2 seconds. And so when you put those two things together, that's the location of the object. And again, the same thing for 3 seconds or for 4 seconds. And that's what we mean when we say that the motions are independent of each other. The horizontal motion is exactly equivalent to what it would be even if it was just moving in a straight line. The vertical position is the same as what it would be if it was just moving in a straight line vertically. And you put those two things together and you get the overall path of the object. in the path of that object is a parabola. So when we shoot an object through the air, when we have projectile motion, the path of the object will be a projectile. In this animation, we have something that's launched up at an angle. This object is launched at a 45-degree angle. The x and y components of the initial velocity are both 60. And you can see in this animation that the x component of the velocity stays 60 meters per second. If you focus on the bottom left at that x component of the velocity, that doesn't change. As time goes on from 0 seconds to 18 seconds, that velocity stays 60 meters per second. But in the vertical direction, the velocity is changing. In this animation, they're rounding negative 9.8 to negative 10. So they're having the velocity change by 10 meters per second every second. So it goes from 60, and then after 1 second, it's decreased to 50, and then 40, and then 30, 20, 10. At the highest point, the y component of the velocity is 0. It's not the total velocity that's 0 anymore. It's only the y component. It stops going up before it starts coming back down. But at the highest point, it is still moving in the x direction. If you look at the vectors on the object, those are the x and y components of the velocity. That y component gets smaller and smaller. Eventually it's 0 at the highest point, and then it points downward and gets bigger and bigger and bigger. That's the y component of the velocity. That x component of the velocity vector, that doesn't change. That stays 60 meters per second. So this means that finding the highest point is going to be just like it was for free fall. We're going to look and we're going to calculate when is the y component of the velocity 0. Here, this happens at approximately 6 seconds. It took about 6 seconds for the velocity in the y direction to go from 60 meters per second down to 0 meters per second. And then it starts coming back down, and it speeds up and goes faster and faster and faster. In this animation, the motion is not symmetric, so you can't look at the time going up and the time coming down and say that they're the same, because it's not starting and stopping at the same height. But when it does start and stop at the same height, we will be able to use symmetry just like we did for free fall. So this picture is showing a common demonstration that's done where you have two marbles. One is in a release mechanism, so it's just going to fall straight down, and the other one, the yellow one, is in a release mechanism where there's a little spring-loaded pin that shoots it out horizontally. And if we look at any time, the height of those two objects is exactly the same. And so this means that the fact that the yellow object was shot horizontally has no effect on its vertical motion. That means if I were going to calculate the time that it took that yellow object to hit the ground and the time that it takes that red object to hit the ground, they would be exactly identical. This is a common question that comes up in physics. You have a gun and it's going to fire a bullet, and you fire the gun perfectly horizontally. And then that's the key. It has to be perfectly horizontally, so there's no y component of the initial velocity. And at the same time you fire the gun, you drop a bullet from the exact same height. And the question is, which one hits the ground first? A lot of people want to say, well, the one that's dropped, because the one that's fired, it takes a long time for it to reach the ground. And that's not true. The bullet that's dropped and the bullet that is fired perfectly horizontally, they both take the same amount of time to hit the ground. The thing that's a little misleading is when you're firing a gun, it's moving very, very fast in the x direction. So in that fraction of a second, if you're dropping it from a height of about 1 meter, that's less than a half a second to reach the ground. In that half of a second, it's going to travel hundreds of meters in the horizontal direction. And so people often say, oh, it traveled really, really far, so it had to be in the air for a long time. And that has nothing to do with the fact that it was in the air for a long time. It just is because it had a very large horizontal velocity. Again, this picture is a very simple example of that, with a spring-loaded gun shooting a ball horizontally and a red object that's just being dropped. But you can set this up with an actual gun. In fact, if you look online, on the TV show Mythbusters, they did this. They set this up. I think you should, if you use Google, I would Google Mythbusters bullet dropped versus bullet fired, and you'll see some clips from that. And it's a really powerful demonstration of this idea. It's very difficult to set that up, and they ran into some difficulties in testing this, but once they got everything worked out, they were able to see that within a few fractions of a second, the time was exactly the same. And that those few fractions of a second were very small compared to the total time. Again, we're ignoring air resistance in this, and air resistance starts to become important with something moving as fast as a bullet. And it's very difficult to get the gun perfectly level, even if it's off by a fraction of a degree. That does change things. So this is the picture that we saw earlier. It's just blown up a little bit more. This is showing the path of the ball, and it's showing the velocity vectors. This shows that the x component of the velocity stays the same during the flight. And the y component of the velocity gets smaller and smaller. At the highest point, the y component of the velocity is 0. So at the maximum height, it's the y component of the velocity is 0, not the total velocity. Again, the total velocity is just equal to the x component of the velocity at the maximum height. If you add the x component of the velocity to nothing, which is what the y component is, you get that x component. Again, in this we see that this x component stays constant. So at the beginning, if the x component is 20 meters per second, at the highest point, the x component of the velocity is still 20 meters per second. All through the flight, the x component is 20 meters per second. And so if you're trying to find the highest point, you look at when the y component of the velocity is 0. If you're trying to find the velocity at a certain time, you need to calculate the x component of the velocity and the y component of the velocity, and then you'll put those together and you'll find the hypotenuse. You'll add two components together. So this is why it was important when looking at vectors to understand how to take x and y components and calculate the magnitude and direction of the total vector. So in projectile motion problems, there's a certain strategy you want to use. First, you're making simplifying assumptions. The main assumption is that we're ignoring air resistance. And then you set up a picture. You set up a coordinate system with the x-axis running horizontally and the y-axis running vertically. You show important points in the motion on a sketch. Things like the highest point, or if it's something that's thrown and it hits a wall, you want to show the wall, where the wall is located, how high up the wall it hits. Define any symbols and identify what you're trying to calculate. In these, you know the acceleration. The acceleration in the x direction is 0. The acceleration in the y direction is negative 9.8 meters per second squared. So the problem becomes one-dimensional kinematics for the x direction and one-dimensional kinematics for the y direction. These equations that are here, we're going to look at those on the next slide, but these are not new equations. These equations right here are the one-dimensional kinematic equations. The only difference is when you're looking at the horizontal motion, we only look at x0, we look at v0x, we look at ax. We only look at the x variables. When we're looking at the vertical motion, we look at y0, we look at v0y, only the y component of the initial velocity, and we look at the acceleration in the y direction. Again, negative g means negative 9.8 meters per second squared. G stands for 9.8 meters per second squared. The thing that links those two together is the time. You can find the time from one of the motions usually and use that value for the other motion. So you might find at what time it reaches the highest point and then how far it traveled horizontally in that time. So you looked at the vertical motion to find the time to the highest point, and then you look at the horizontal motion to find out how far it traveled. Or maybe you want to know when it reaches the ground, how far it traveled. So you look at the vertical motion to figure out at what time the height is 0 again, and then how far it travels horizontally. Or maybe you throw something towards a wall, so you know what the x value is later, so you figure out at what time is it at a horizontal position of 20 meters, and then you can calculate what is the height at that time. And then you always want to check that you have the correct units, make sure your answer is reasonable, and then make sure that you're answering the question. That's especially important with these because there's often going to be more than one step, and you need to make sure that you actually went through and found the answer to your question. So again, in the horizontal direction, this is using the equation for position as a function of time. In one dimension, we said that x equals x0 plus v0t plus 1/2 at squared. Well, with this, when we're looking at two-dimensional motion, this v0 becomes v0x. It only becomes the x component of the initial velocity. And this a becomes the x component of that acceleration. And because the x component of the acceleration is 0, that term is there. So usually I'm going to not include it, but we have a plus 0 there. Again, this v0 cosine theta 0, that was just v0x. We had our initial velocity v0, we broke it into components, and this x component was v0 times the cosine of theta 0. So that's not a special equation, that just says find the x component of the initial velocity and use your position versus time equation for one-dimensional motion using only the horizontal quantities. In the vertical direction, again we have v0, this initial y velocity is v0 times the sine of theta 0. So this first equation is equivalent to our v equals v0 plus at equation that we had for one-dimensional motion. But now, because we're looking at the y motion, this becomes vy, this becomes v0y, this becomes ay. So we have that the y component of the velocity equals the initial y velocity. Again, this is this y component of the initial velocity plus negative 9.8 meters per second squared times t. So negative g is negative 9.8. The second equation, again, that's that same position time equation. So now we have that the vertical position y equals the starting vertical position y0 plus the initial vertical velocity v0y times t plus 1/2 times the vertical acceleration negative g, or negative 9.8, times t squared. So again, we only look at the y components. And so this v0 sine theta 0, that's just this y component of the initial velocity. And so we go through and we plug in those values. And then that last equation is the equation that relates the velocity to the displacement. In one dimension, we had that v squared equaled v0 squared plus 2a x minus x0. Well, now this is the y component of the velocity squared equals the initial y velocity squared plus 2 times the acceleration, negative 9.8, times the change in height of the object. So let's look at this for one problem. An object is fired from the ground at 10 meters per second at an angle of 30 degrees. So we're first going to draw a picture. We have the ball starting at the ground. The initial velocity is 10 meters per second. This angle of the velocity is 30 degrees. And this ball is going to go up and it's going to come back down. And so the first question is asking for the horizontal and vertical components of the initial velocity. So that means that I'm taking this velocity, initial velocity of 10 meters per second, and I'm breaking it into x and y components. So this x component would be 10 meters per second times the cosine of 30 degrees. Again, the cosine of 30 degrees equals the adjacent side, v0x, over the hypotenuse of 10. So that x component was 10 times the cosine of 30 degrees, which is 8.66 meters per second. This initial y velocity, again, the sine of 30 degrees equals v0y over 10. So v0y equals 10 times the sine of 30 degrees. The sine of 30 degrees is 0.5. So this is 10 times 0.5, or 5 meters per second. So the x component of the initial velocity is positive 8.66 meters per second. The y component of the initial velocity is positive 5 meters per second. Again, it's moving to the right in the positive x direction, and it's moving up in the positive y direction. Then part B, how long does it take to reach the highest point? So again, we have to know that the highest point is referring to when is the y component of the velocity equal to 0. So we set up our horizontal column. I'm going to let this start at the origin, x equals 0 and y equals 0 at the start. The initial x velocity is 8.66 meters per second. The horizontal acceleration is 0 meters per second squared. In the vertical direction, I have that the initial height is 0. The initial vertical velocity is 5 meters per second. The vertical acceleration is negative 9.8 meters per second squared. And so this is saying at what time is the vertical velocity equal to 0 meters per second. This is identical to a ball is thrown upwards at 5 meters per second. At what time is it at the highest point? It's exactly equivalent. So we're going to look at the equation for velocity and time. So we have Vy equals V0y plus the vertical acceleration Ay times t. So if I plug in those values, I have 0 equals 5 meters per second plus negative 9.8 meters per second squared times t. Or the time would be 0.51 seconds. So notice we didn't do anything with the horizontal direction. The highest point that had everything to do with just the vertical motion.